Yes, hi, this is George Raksangian, and today I would like to talk about conservation of energy. So, let's start as always with the brief theory. Uh, so, the only theory you need to know about this topic here is that delta E has to be equal with the work of non-conservative forces. So that means that the difference in the mechanical energy has to be equal with the work of non-conservative forces. And on the left-hand side of the equation, we can put kinetic energy, which is of course equal with 1/2 mv square, where m is the mass and v is the speed. We can also put potential energy due to gravity, which is mgh, where again m is the mass, g is the acceleration of gravity, and h is the distance from the point that we consider zero for potential energy. And let's put also the elastic potential energy, which is 1/2 kx squared, where k is the constant of the spring and x is the distance from the position of equilibrium of the spring. So that's on the left hand side of the equation. Now on the right hand side of the equation, you have all the non-conservative forces, and for the topics that you will be doing problems, non-conservative force is anything that has to do with resistance, so that of course includes friction. If you are in a fluid like air, of course it's drag. In general, any force of resistance. So that's about the theory. So let's continue with an example. So let's do an example, a simple example. For making this easier and faster, I will not use numbers. I'm pretty sure everybody knows how to deal with numbers, and of course we have calculators. So let's assume that we have a guy that is sliding down an incline, and let's say that the distance of the incline is d. The angle with respect to the horizontal of the incline is theta, the mass of the guy is m, the initial velocity of the guy, which is the velocity at the top of the hill, it's v0, and the velocity at the end of the incline is v final. So that's what is given, and what we're trying to find, the work of friction and also the coefficient of course kinetic friction, nu k, between the guy and the incline. So let's do a small diagram. So let's say this is the incline. Let's say this here is theta, and let's say that this distance here is d. And you have, let's say, the guy here. This is the initial position. Let's say O, and this is the final position. Let's say F. So, according with the theory that we stated a little bit earlier, what we have to apply the theory that applies in this kind of problems, which said is that delta E has to be equal with the work of non-conservative forces and of course, I need to say that here the guy is going down. Of course, if we're looking for a new K, the guy, there is a friction between, just to make sure there is a friction between the guy and the incline. So, delta epsilon, so in this case, this we said is the final and this is the initial point, so that means that E at final minus E at the initial has to be equal with the work of non-conservative forces. So E final. So at this point here, we consider here the point where the gravitational, where the potential energy due to gravity is equal to 0. So that means that in this point we have no potential energy, so or 0, and so that means that the only other energy we can have is kinetic energy. So the kinetic energy at point F, it will be 1/2 m v final square. And now the energy at this point here, in this point, of course, we have kinetic energy, because the object is moving with velocity v0, so it's 1/2 m v0 square, plus of course we have potential energy because it is at some height h with respect to the 0 level of potential energy, so that's plus mgh, so that should be equal with the work of non-conservative forces, and the only non-conservative force that we have here is the force of friction, and of course kinetic friction. So we have to erase again. We can take the brackets off, so that means that here we have a minus, and now the only thing that is missing, h. Of course h is easy to calculate. We know d, so that means that we know d, we know theta, so that means that the sine of theta has to be equal with h over d, so that means that h has to be equal with d sine theta. And if we can write this again, we have that 1/2 m vf square minus 1/2 m v0 square minus m g, and we said the h is equal with d sine theta. So that's the work of friction that we're trying to find. And of course we know everything, the mass, the initial and final velocity, the d, the theta. So that's the answer for the first question, which is what's the work of the friction. And now, we're looking also to find for the coefficient of kinetic friction. So let's erase here. So we already know WF. So now, we have to use a little bit Newton's laws, which is of course something that you're supposed to know if you're studying conservation of energy. So what we have here, we have, let's say, let's do it here. So we're on it's more clear. So let's say here we have the guy. So what are the forces that are exerting on the guy? It's the weight, of course, which is W. And of course you have the normal force from the incline to the guy, and of course you have the force of friction, and because the guy is going downwards, of course the force of the friction is always in the opposite direction, so that means that force of friction, it will be here. So these are the three forces, and of course we just have to analyze. We have to analyze the weight. So if you analyze the weight in two composite forces, so the one it will be this and the other it will be this, so that will be the Wx, and this here will be the Wy. And of course, since the object is not moving, and of course it's not accelerating in the y direction, that means from Newton's laws that the sigma f of y has to be equal to 0. So what are the forces in the y? It's the normal force, and it's the Wy, so this has to be equal to 0. And now how much is Wy? From this small triangle here, of course this angle here is theta, and this is why this is theta, because this angle here and this angle here, they have their sides perpendicular. This side here is perpendicular with this side, and this side is perpendicular with this side. So when two angles, they have their sides perpendicular, they are equal, so that means that this angle here is also theta. So, and we're looking to find Wy, so we have to take the cos of theta. So cos of theta has to be equal with Wy over W. And of course from that we have that Wy is equal with W cos theta, which is equal with mg cos theta. And okay, and now we have to find the coefficient of static friction. So we know that the force of friction, and in this case the kinetic friction, has to be equal with mu k, the coefficient, times the normal force. So the normal force we know here is mg cos theta. So from that you can get that mu k, which is the coefficient of static friction, has to be equal with Fk, which we already know from part A of this problem, over mg cos theta. So that's about it, about the conservation of energy. So thank you very much for taking the time to view this video, and I hope you find it useful, and bye for now.